Hello, Math Humans. We're going to do 5.5a. Today we're going to be doing bases other than e. Our objectives are that we're going to review exponential growth and decay, and then we're going to differentiate and integrate functions that have bases other than e. So if you will remember, exponential growth from pre-calc is y is equal to a b to the x. If b is greater than 1, then it's growth. A is the initial value, okay? And if it's decay, if b is less than 1, then it would be decay. Alrighty? If we do half-life problems, your equation is going to become y is equal to a times a half, because the rate of decay is a half, and then it's going to be raised to the x divided by the halving time. That's a weird word, but whatever your exponential function is, the decay, you have to divide by what that decay period is. There's a second equation, and you often will see this one in calculus. It actually doesn't matter which you use. Calculus tends to use this one more. This is growth if your k is positive, and it is decay if the k is negative. Okay. Another way to see this equation written is y is equal to ae to the bx. That would have been, I think, the way that we saw it in pre-calc. We're going to talk about how we develop this as we do some of these problems. So example number 1 says that the half-life of carbon-14, which is the element that they use to date things, is about 5,715 years, which is fascinating. A sample contains 1 gram of the carbon. I was going to put an initial, but I don't know if that's right because I don't remember my periodic table well enough. How much will be present in 10,000 years? 10,000 years. Alrighty, so again, you can choose to use whichever formula you want. For half-life, I tend to use this formula because I think it's just a little bit more straightforward. So we'd have y is equal to a. I don't know the initial amount. Oops, I'm sorry, I do know the initial amount. I'll put it in a moment. 1/2 in t, and then my halving period is 5715 years. My initial amount was 1 gram, so I have to the half, and then times t divided by 5715. Well, if I want to know how much is present in 10,000 years, all I have to do is substitute my 10,000 in here. So I would get y is equal to 1 times a half times the 10,000 divided by the 5715. And it's going to be 0.30 of a gram. So just a tiny wee bit would be left after 10,000 years. Alrighty, more information that we need to remember from pre-calc maybe might be the change of base formula. And so many of your calculators don't need you to use the change of base formula anymore, but it is still a good thing to remember just in case. So the log base a of x means that sometimes I can't put this in my calculator depending on the age of your calculator. So I could do the log, actually I'm going to do the natural log of x divided by the natural log of a. So I can choose a base, in this case I chose e, to work in my favor. The next thing that we want to talk about are the properties of inverse functions. Okay. And again, this is just helping us remember information that we learned last year. So the first one is y is equal to a to the x if and only if x is equal to the log base a of y. Okay, and so that's just converting the forms. Number 2, a log base a of x is equal to x for x is greater than 0. And then the third one would be the log base a of a to the x is also equal to x for all x. So those are just things that occasionally you see, and they might tend to confuse you a bit, but it's just a property, and we want to remember those. Example number 2 says solve. Yeah, math. Woohoo, we like solving. I get 3 to the x is equal to 1 over 81. So there's lots of different ways that you can solve this problem. One method would be, I'm going to rewrite this as 3 to the x is equal to 3 to the negative 4. I solve the baby equation at the top because the bases are the same, and I get x is a negative 4. The other one would be to take the natural log of both sides, and the properties of logs would have that the exponent goes out front, so I would get x natural log 3 is the natural log of 1 over 81, and then solve for x, and it's the natural log of 1 over 81 divided by the natural log of 3. Either method is appropriate. This one probably saves you a little bit of time. Okay? So now let's get some of our rules for derivatives. So these are derivatives for bases other, that's an E, other than E. And again, these are already on your formula sheet, but it is good to know how to manage them. So if I have the derivative of a to the x, that's going to be the natural log of a times a to the x. Number 2, if I have the derivative of the log base a of x, that's going to be 1 over the natural log of a times x. Okay. The third that we're going to have is d over dx. A to the u is equal to the natural log of a times a to the u, and then times u prime. So we always bring in this particular type of rule with the u's. Notice that the variables don't match, just to help you remember that you need to do the chain rule. And then number 4, the derivative with respect to x of the log base a of u is 1 over the natural log of a times u prime. And again, the reason that we do those is to help us remember to use the chain rule. All right. Example number 3, cruising right along. So if I have y is equal to 2 to the 3x.
Please have a custodian go to room 305. Please, a custodian to room 305.
There's your public service announcement for the day. Woohoo! Sorry. So you want to take the derivative. So my derivative is going to equal the natural log of 2, because it's a base other than e, times 2 to the 3x times the derivative of the top. There's my chain rule 3. And so I'm going to write this as 3 natural log 2 times 2 to the 3x. You could go one step further and turn this into the natural log of 2 to the 3rd times 2 to the 3x, which would be the natural log of 8 times 2 to the 3x. I think this is sufficient, but if you were doing a multiple choice portion of a test, they might push you to remember the extra properties of your logarithms. All right, example number 4. I'm going to have y is equal to the log base 10 of the cosine of x. Remember, this is a standard log. I don't have to write the base, but just for points of illustration, it's helpful to remember. And I want to take the derivative. So my derivative is going to equal 1 over the natural log of 10 times the cosine of x in the denominator times the derivative of cosine, which is a negative sine of x. So I would write that as, notice I have sine divided by cosine, a negative tangent of x divided by the natural log of 10. Alrighty, now we're going to get our integration rules for bases other than e. So integration rules for bases other than e. Okay, and again, these are all things that are on that formula sheet. It just needs to be added to your memory skills. So 1 over the natural log of a times a to the x plus c. Okay, and then we would have to do u substitution if I have things attached to my x. So let's do another example. So let's do, I think we're up to example number 5. And I have y is equal to x raised to the x, and I want to find y prime. Okay, so there's not really a set rule for this, so I'm going to take the natural log of both sides. So I'm going to say the natural log of y is x natural log of x. Okay, now I could take the derivative of both sides. 1 over y dy is equal to, and this becomes the product rule, the first thing times the derivative of the second plus the second thing times the derivative of the first. X divided by x is going to go to 1, so this is going to be 1 plus the natural log of x. We're trying to find y prime, so I need to isolate the dy dx. Okay, so that should have had a dx in there, my bad. So I'm going to multiply both sides of the equation by y, so I'm going to say dy dx is equal to 1 plus the natural log of x times y, but I know what y is, so I'm going to rewrite this as 1 plus the natural log of x times x to the x, because that was the original given problem for y. Alrighty, let's move on and do another example. Let's do example number 6. And I'm going to have f of x is equal to 3 to the 2x, and I want to find the derivative. So my derivative, f prime of x, is going to equal the natural log of 3 times the original thing times the derivative of the top, which is 2. So this is going to be 2 natural log 3 times 3 to the 2x. And again, if you wanted to go one more step, you could write this as the natural log of 9 times 3 to the 2x. You can stop here unless maybe that solution's not there when you do a multiple choice problem. Alrighty, I have a couple more examples and then we're done. So example number 7 says g of t is equal to the log base 2 of t squared plus 7 raised to the third power, and I want g prime of t. Okay, so when I do g prime of t, I'm going to get, and actually before I start doing that, my bad, I want to rewrite this as I look at the equation. I'm going to use my properties of logarithms to pull this out front because it's going to make my math life easier. So I'm going to say g of t, exponents go out front, is the log base 2 of t squared plus 7. So now when I do g prime of t, okay, it's going to be, the 3 is a constant, so it just stays, over the natural log of 2 times t squared plus 7 times the derivative of the inside, which is 2t. So this is going to be 6t over the natural log of 2 times t squared plus 7. And that wasn't so horrible. All right, one more example, and then we are done for today. Example number 8. I'm going to do the integral of 5 to the negative x dx. Well, when I do this, I'm going to let u equal a negative x. My du is a negative dx. I need to introduce the negative, so I'm going to make a negative integral 5 to the u du, and this is going to equal, here's the negative, and then I have natural log of 5 to the u plus c, and then I would report my answer well, so I would say the integral of f of x dx is a negative 1 over the natural log of 5 times 5 to the negative x plus c. Alrighty, that's it for today. I will see you soon.